we now move to high energy density conditions, and this is a talk from Emma McBride at Queen's University, Belfast. Emma.
Okay, thank you. Okay, well, this is a bit of an extreme condition in of itself, standing up on stage at the Royal Society, but it's a real pleasure to be here today. So I've recently moved to Queen's University, Belfast as a Future Leaders Fellow, and I'm delighted to present our working group what we think are great science opportunities that a UK XFEL would afford our field. And so I just want to thank a lot of people who've done a ton of work on this, many of whom are here today in person or online. That's Andy Higginbotham at York, Andy Comley at AWE, Sam Vinco and Justin Wark at Oxford, Malcolm McMahon at Edinburgh, and my colleague Marco Borghese at Queen's. So why do we care, first of all, about matter at extreme conditions? Well, understanding how matter behaves at high pressures and temperatures is important for many different fields of science. So geophysics, planetary science, astrophysics, looking at the dynamic strength and failure of materials, looking at a search for novel materials themselves or pathways to fusion energy. So that's just a few things that we're interested in. So most of the matter in the universe, in fact, exists at high pressures and temperatures in the core of the Earth itself, or at even more extreme conditions inside, say, Jupiter or any of the thousands of exoplanets out there in the universe. So I think galactic science was alluded to earlier, and I guess that's me. So yeah, we'll see what we can do. So at these extreme conditions inside Jupiter or within stars, matter exists in a state known as warm dense matter. So this lies in a region of phase space in between condensed matter and plasma physics, but it's not well described by either theory. And so that's why we need a really robust experimental interrogation of this state to understand how things are going on inside these planets and stars, but also to build a robust and predictive theory. So we also created in the lab on Earth in inertial confinement fusion experiments. So if we want to harness fusion as a clean and renewable energy source, understanding matter at extremes is essential. So we created in the lab by a variety of techniques. So nanosecond shock compression, using femtosecond optical lasers to heat matter. We've also heard a little bit about using secondary sources. We use energetic electrons, ions, or protons to heat or damage materials. And we can also use the FEL itself to generate extreme states of matter. So what these all have in common is that they create highly transient states of matter. So each laser target interaction in our experiments is a unique experience. And the extreme states exist for a few picoseconds out to a few nanoseconds in duration. And they often have a large amount of free electrons, which means they're challenging to probe optically. And that's, of course, where free electron lasers come in. I don't need to tell everyone here that they produce extremely bright X-rays that are time resolved, and they can capture these highly transient, highly ionized states. And to date, there's 3 facilities around the world that couple high intensity laser drivers with hard X-rays that have really revolutionized this field. So we've done X-ray imaging and X-ray diffraction, different X-ray spectroscopy techniques. And there's a strong UK community that have played a leading role in a lot of these experiments, leading them or strongly collaborating on a lot of this work that's done. And so our working group has identified 4 key areas that the UK can play a significant role with its own hard X-ray FEL. So these are detailed in the science case, if you want to read about them. But very briefly, section 4.1 on shocked materials and matter at extremes, section 4.2 on quantum plasmas, so that's warm or even more extreme hot dense matter. Section 4.3 is X-ray interactions with electrons, protons, or ions. And 4.4, quite future looking, even more future looking, I would say, to even more extreme conditions at a spherical compression facility. So I could talk all day, but I've been told we're not allowed to do that. So I will just very briefly give you an idea of the science we've done so far and hopefully where we want to go in the future. So sticking first with shocked materials or matter at extremes. So I've got a little pressure diagram, or pressure cheat sheet, I should say, up there on the top right, if you're not familiar at thinking above 1 bar. So hopefully that's helpful. So I'll start by saying that static compression techniques at 3rd generation synchrotron light sources have already provided a huge amount of information about how matter behaves at extreme conditions. And in the last few decades, what they revealed was that as you compress matter more and more, it doesn't become more metallic or simple. It actually, as you compress it to around a megabar of pressure, core valence electron interactions play an increasing role, and you get weird low symmetry structures with non-metallic character that are stabilized. So this was observed experimentally, and then the theory groups went to super extreme pressures far beyond megabar, tens of megabar, into the terapascal regime, far beyond what static compression methods could reach. And Chris Pickard's group at Cambridge discovered that even simple systems like aluminium form these weird low symmetry structures if compressed enough. And carbon, in fact, is supposed to crystallize into a structure that is harder than diamond and may be recoverable to ambient conditions. Now, these pressures are beyond static techniques, but they are accessible using laser-driven compression methods. But the question remained, can you observe them on nanosecond timescales? Well, that work was addressed by Malcolm McMahon's group at Edinburgh through a series of experiments at the MEC end station at LCLS. So just a typical schematic of an X-ray diffraction experiment is shown here on the left. And this is really a workhorse diagnostic in this field. And on the right, you can see a one-dimensional diffraction pattern from laser compressed antimony. And so with the hard X-ray FEL, you can see a forest of peaks that Malcolm and Amy Coleman, who's the first author on this work, were able to ascribe to the low symmetry structure that you can see in the inset here. So they observed that on nanosecond shock compression, you can observe these low symmetry complex structures, which is great, but this was at relatively modest pressure. We're interested in even more extremes. To stick with diffraction, this is work I did with Andy Higginbotham on silicon, which is a clearly important technological material. And what we learned in our shock compression work is that solid-solid phase transitions on shock compression were shifted to lower pressures than those observed statically. And then other studies observed a shift to higher pressure in different systems, or the absence of some solid-to-solid phase transitions. So we really need a thorough and robust study of these systems, how kinetics and shear play competing, are impactful on the phase diagrams at extreme conditions. And of course, we're interested in going to the center of the Earth and beyond. So all the things I've shown you so far are below 1 megabar in pressure. We're interested in going to 3, 10, 100 megabar if we can, to see how matter behaves at really extreme states. And what's important here is as we compress systems in real space, they're going to get bigger in reciprocal space. So all our Bragg peaks will shift to higher Q. And so hard X-rays in the 20 to 30 keV energy range are essential for us to understand the structure of matter at these conditions. And also you can see, we see a diffuse peak on the top left of our diffraction pattern, where we're saying we observe single shot melting, but if we want to make quantitative measurements of the liquid density and local structure, we also need to extend our Q range significantly, and harder X-rays is how we do that. So very briefly on to section 4.2, Emel already mentioned that XFELs can be used to generate extreme states. Here in this work by Sam Vinko and Justin Wark, they micro-focused the XFEL down to intensities of over 10 to the 17 watts per square centimeter. And instead of using it to probe the extreme state, they used it to generate. They generated temperatures in a solid density plasma of around a few hundred of EV. So by combining this with K-alpha emission spectroscopy, they were able to look at the collisional dynamics and ionization potential depression in these warm or hot dense plasmas relevant to modeling the interior of stars. Now, of course, it's pretty clear that higher pulse energies and the ability to nano-focus the beam will get us to even more extreme states of matter here. Another example from Sam is his work using two-color XFEL, Marcus mentioned, and we're also very excited about the prospect of a two-color XFEL. Here, he used it to generate a warm dense state in hundreds of nanometers of, I believe, aluminium, and then to probe the X-ray transmission of the sample with a second pulse. From this, the opacity was determined, but of course, with hard X-rays, instead of pumping hundreds of nanometers of a sample, we can pump microns thick samples and probe the dynamics of them. And a two-color XFEL combined with high-intensity lasers will allow us to make simultaneous measurements of X-ray structure, the electronic structure with spectroscopy, and looking at the macroscopic behavior of the system through imaging. As I said, every laser target interaction is a new experience, so we need as many diagnostic probes at the same time, and a two-color FEL would be a huge benefit. Okay, so sticking with spectroscopy for a moment, another important diagnostic we have is inelastic X-ray scattering. So depending on the energy transfer range you look at, you are sensitive to different phenomena. So with the seeded beam mode of operation with a bandwidth of around 1 eV, we can happily measure plasmons in our samples, or of course Compton scattering from electrons. What we've recently become interested in is measuring in the tens to hundreds of milli-electron volt range that are characteristic of phonons in solids or ion acoustic modes in a warm dense plasma. So by measuring down here at this low energy transfer, or yeah, low, we'll say low, we'd be able to measure thermal diffusivity, viscosity, material sound speed, and perhaps even the ion temperature of our system. So we've had some success with early experiments here, but you'll notice that these energies of 100 MeV are much lower than the seeded beam mode. So we have to use a high resolution monochromator with the XFEL, which throws away tons of our photons. And of course, we don't want to do that because inelastic scattering is very photon hungry. So of course, something like an XFELO or some scheme that will give us near transform limited pulses will be a huge benefit to these transport property measurements. So I'm going to go very quickly through my last few slides, especially because James is going to talk a bit more about secondary sources later, so I don't have to, but high intensity lasers don't just heat and compress. We can use them to generate beams of electrons or protons and ions. And again, we've heard a bit about this already, but by combining it with an XFEL, we can look at real-time damage to materials that are relevant for, say, magnetic confinement fusion experiments, looking how damage and the lifetime of these reactor wall materials behave. And then looking to the future, to even more extreme states at a spherical compression facility, we wouldn't anticipate this would necessarily be a day one priority, but of course we want to go to the most extreme states we can in the universe, where we get fusion as well as understanding stellar cores. I would say what's important at this point is to learn lessons from the facilities that have gone before us and make sure that we have enough space for a viable upgrade path. They're very expensive. I just moved from Slack, so I know what I'm saying. There's very extensive digging, excavation work going on there for the MEC upgrade project. And of course, we'd like to avoid that. And this is my slide with all the text, but you've heard a lot of what I've said already. We would like variable X-ray energy up to 30 keV or more if we can get it. As many photons in a pulse as you tell us we can get, that would be great. Pulse lengths from 0.1 femtoseconds out to 100 femtoseconds, and variable bandwidth from tens of eV down to tens of milli-electron volt would be great. Two-color FEL would be fantastic. We're very excited about that. I haven't mentioned polarization control. That's also important. And of course, a high degree of synchronization between the XFEL and high power lasers. And again, James will talk about high power lasers, but I just want to say that the CLF have developed world leading state-of-the-art laser systems. One is being commissioned at European XFEL right now as their shock compression driver. And it's already, one's operating, I believe, at Highleys in Prague, and it keeps breaking records as far as I can tell. So that's very encouraging. So we've got a lot of expertise in building the lasers and also using them with hard X-rays to do some interesting science. Well, I hope I've convinced you it's interesting science. With that, thank you for your attention.